everyone. My name is Wang Yijing. I'm an undergraduate from Tianjin University in China. The paper I will be presenting today is titled Based on Revit Simulation to Propose a Green Building Design Proposal, a case study in Mérida, Mexico. Governments around the world have introduced policies to promote green buildings. However, specific practice-oriented design solutions are still rare, especially for hot and humid climate zones. This study focuses on Mérida, Mexico, a city with a tropic savanna climate, to fill this gap. Our goal is to propose an integrated design strategy combining building value, glass type, and orientation to improve energy efficiency in green hotel design. So, why Mérida? First, the annual average temperature is high. Cooling is the dominant energy demand, not heating. Second, the humidity is extremely high. This not only makes people feel uncomfortable, but also forces air conditioners to consume extra energy for dehumidification. Third, the temperature difference between day and night is small. This limits the effect of natural night cooling. In short, Mérida urgently needs a building design strategy that effectively reduces cooling loads. We use Revit for both 3D modeling and energy simulation. We compared 3 types of architectural volumes, 3 types of glass, 3 orientations. The output indicator is cooling and heating energy consumption per square meter, managed in gigajoules. The first vulnerable is building form. Design 1 is low and linear. It is open but fully exposed to the sun. Design 2 is low and enclosed. It creates an internal courtyard. Design 3 is vertical and concave. It has large volume, but also large heat gain surfaces. The simulation shows that Design 2 performs best. Why? First, the enclosed form provides large-scale shading. It significantly reduces direct solar radiation on facades and the courtyard. Second, it creates a cold well effect. Cool air accumulates at the bottom of the courtyard. When this pre-cooled air enters the rooms, it directly reduces the cooling load. Third, in winter, the enclosed form resists cold wind and traps solar heat, like a warm sun trap. So, the enclosed building is not only energy efficient, but also creates a self-adjusting microclimate. The second vulnerable is glass. We tested 3 types. Glass 1, double clear glass, high SHGC, high U value. Glass 2, low E glass for hot climates, medium SHGC, medium U value. Glass 3, high performance, low E glass, lowest SHGC, lowest U value. 2 parameters are important here. SHGC, solar heat gain coefficient. The lower it is, the less solar heat enters the building. U value, heat transfer coefficient. The lower it is, the better the insulation. In Mérida, low SHGC is more important than low U value because solar radiation is the main source of heat gain. Glass 3 blocks the most solar heat and achieve the lowest cooling consumption. The third vulnerable is orientation. North-facing has the lowest heating demand, but the highest cooling demand, because it cannot remove moisture effectively. East-facing receives strong morning sun. Cooling load increases in the early hours, but there is some afternoon shading and ventilation. South-facing achieves the lowest cooling consumption. In summer, the sun is high. South facades receive minimal direct radiation. In winter, the sun is low. South facades capture useful solar heat. We also consider site design. The river can help cool the environment if used properly. The road may contribute to the urban heat island effect. Our solutions are to use coarse ventilation, create airflow between the water and the site to remove indoor heat, and to plant trees around the site, create a green buffer zone for shading and heat island mitigation. We also propose introducing water bodies into the courtyard. This lowers the temperature without adding extra moisture. So here is our best recommended configuration. Building volume, low and enclosed. Glass type, high performance, low E glass. Low SHGC, low U value. Orientation, south facing. Site design, water bodies, green buffer. This configuration achieves the lowest comprehensive energy consumption and is well adapted to Mérida's hot, humid climate. However, this study has limitations. First, the conclusion is based entirely on static Revit simulations. We did not consider human behavior, equipment efficiency, fluctuations, and differences in local construction quality. Second, we have not conducted an economic feasibility analysis, such as initial investment costs, material availability, or maintenance complexity. In the future, we hope to monitor a real building to validate actual energy performance. Conduct a life cycle cost assessment. Despite these limitations, this study provides a replicable design reference for green hotels and even other public buildings in Mérida and similar hot humid regions. It demonstrates how simulation-based design optimization can support climate-responsive architecture. Thank you for your attention.